So now let's talk about some new things. We can sort of make sure we got a common base for everything, and we can now talk about some new stuff and move ahead and sort of take a turn away from typical stats and sort of how stuff directly applies to classical tests. So far, everything sort of applies to any use of statistics in social sciences. Sort of has the same base. A lot of the stuff we're talking about here, we're going to talk about stuff that's specifically about test theory and things like that. So the first thing we'll talk about is something called classical test theory, and how estimates of things like reliability for items at a test have been developed with this classical test theory as a lens. I should mention the reason why it's called this term classical that's here. It used to just be test theory. Right? It used to just be test theory. That's it. So there was test theory, and it got shifted to something called classical test theory because there's a newer game in town, sort of, so to speak, which is called item response theory. That is seen as the sort of modern test theory. So because this is the more modern test theory, they rebranded this as sort of classical test theory. Make sense? So we're going to start off talking about classical test theory. We're not going to have time to really go into item response theory, because that could be a whole class in and of itself. It's much more mathematically intensive, computer intensive. So we're going to stick to stuff that's sort of simple. And the truth is, even item response theory will be built, like if you do an analysis of items based on IRT, which is what this is oftentimes referred to, IRT. If you do analysis of items based on IRT, you're going to first start with CTT. You're going to start with classical test theory, figure out things that are working and that don't work with classical test theory, because it's so much simpler to do, and then move to confirming that the items are sort of functioning the way they're supposed to with item response theory, which is the step we're not going to get to. Okay, like I didn't see anything about item response theory until my doctoral program, because it's sort of an advanced methodology that builds upon all kinds of stuff. You got to know logistic regression, a bunch of other things. You got to know factor analysis and other things all combined together. But this is just to sort of give you an idea. Why is it called classical test theory? Well, because it used to just be test theory until a new game came in town and sort of changed things. Okay? So let's start with test theory as the way it sort of began. And what assumptions do we make, and how do we sort of proceed? So as theories and assumptions, we'll talk about types of reliability, and we'll go through some examples of how it works. Okay, so classical test theory is oftentimes referred to as something called the true score model. True score model, which we'll talk about. It's called classical because that's relative to item response theory, which is seen as more modern, which I just said. So classical test theory, I mean, it's a theory, but really it's like a set of psychometric procedures that we use to test items, to look at scale reliability, to look at item difficulty, item discrimination. It's just a bunch of procedures that we use to sort of test items and to look at tests as a whole. There's a whole bunch of these things. But they all sort of fall under the same idea of a true score model that is what we're going to discuss first. And this is where things get a little theoretical and a little bit sort of in the weeds. So ask lots of questions if it doesn't make sense, and I'll try my best to explain. Classical test theory it's still used, even though we refer to it as classical test theory as if it's, it was done in the Renaissance or something. It's really just, it's just a simpler set of assumptions that people use for a long period of time that have their issues with it, but for the most part they still work fairly well for lots of different things. The nice thing about them is they're simple. Most everything you need to do with them is readily, easily available in stats. You can do it in Excel, right? Simple stats can be done in Excel. They can even be done by hand. If you can compute correlation, mean, standard deviation, those types of things, you can actually do any of this stuff by hand. It may just be a while, because if your test has 30 items, you're doing it 30 times. Actually, probably more than that. If you're doing correlations between them, it could be quite a lot. So most everything we need is actually done fairly simplistically with the stats that we reviewed. Mean, standard deviation, percentages, like percentiles, correlation, regression is all you really need to know. So you don't really need to be a statistical genius. With something like IRT, you now need a much more advanced understanding of sort of the mathematics, things like derivatives, things like iterative solutions, and things that have become a lot more complicated. It's a lot more mathematically and computationally intensive, which is why people still like classical test theory, because it's very simple and the ideas are very easy to apply. Okay. The CTT analyses are performed on the test as a whole rather than on the item. Even though we will do item statistics, it's still going to be relative to the test as an intact test. Okay. They apply only that group of students on the collection. So this is what the limitations are. Any reliability or item statistics that we run are only relative to that item being with the other sets of items that are there, and only relative to the respondents, the people who actually took that test. Which means if you take it to other places, you take it to other sets of respondents, you take it to, you include it with different items, you may get different results. So it has limitations in how it can be applied. All right. All right, so here is the basis of the true score model. It's going to sound overly simplistic that an entire theory is based on this idea, but you'll see it becomes a little more complicated as we start to apply it. So what this assumes is that every person that you're measuring, it doesn't matter what it is, depression, whatever, height, it doesn't matter what it is, right? If you're measuring something on somebody, it assumes that everyone actually has a true score. There's actually a real true score for that thing on that scale. The problem is, the scale itself is not going to be perfect. You're going to be measuring the true score that person has, plus or minus some variability, which is usually called measurement error, right? There's going to be some measurement error involved in sort of measuring that thing that's going to either add or subtract from the person's true score. So that's it. The common true score model is a person's score on using a measure, whatever measure, scale, the tape measure, whatever thing you're using to measure something, you're going to get a number or value for that. That value is going to consist of the true value, the true nature of that thing for that person, plus some measurement error that is inherent with these scales that we use. So every response to a survey is a person's true score plus error. Every scale you use to measure your weight is your true weight plus or minus error. Everything that we measure is going to be imperfect. Some amount of true, there's going to be some true score there, plus or minus some error. With me so far? Seems like a pretty simple assumption, right? We measure stuff. It has, the person's true score is there, and it's going to have some measurement error. But here's where the trick comes in. How do we separate these two out? How do we figure out what is error so that we can remove it and get the true score alone? The better job, the better a scale is at identifying and separating out the error, I should say not the scale, but the approach to analyzing the scale, the better it is at sort of pulling out the measurement error and getting the true score alone, the sort of more valid that thing is at measuring the true score. So far? Okay. So far so good? You have questions? All right. Cool. So based on, in terms of like expected values or expectation, it gets a little weird. But the idea is that, go back to here a second. If the person's score on a scale is really the true score plus error, right? If I were to give the person the same scale over and over again, you would think that the sort of long run average of that person sort of taking that scale over and over again, like if you were to weigh yourself and for whatever reason your scale sort of just has a plus or minus a certain amount of error to it, if you weigh yourself over and over again and you took the long run average of those weigh-ins, you would likely be able to capture that true score pretty well. because you can actually, you're allowing the average to sort of counteract the measurement error and sort of being averaging those things out to what the true score looks like. So what this is saying is some of the assumptions under the true score model is the expected value of any score on a test for an individual person is just their true score. So the long run average, if you were to do that over again, would be the true score. So this is what we expect their score on X to be, is really their true score. If only we could get rid of the measurement error, we'd be able to measure their true score right away, which means that the difference between their actual score on the test and their true score is what we are saying is error. So error can be just the difference between their score on the test or on the scale, on the item, and their actual true score. That difference is really what we're talking about in terms of measurement error. So since the expected value for these two, the difference between score and a true score is really the expected value of X. Expected value of X is T, right? Expected value of X is T. The expected value of T is also T. So in the long run, if everything's done correctly, the measurement error should sort of cancel out to sort of zero, meaning that we're not expecting any biases, right? So that if there is measurement error around X, it is sort of plus and minus around T, so that in the long run, the difference between these two things really should be, these two things should be about the same. We should really be getting zero error if we're expecting it to be. So what that really means, and it sounds like it's a lot of jargon, a lot of words, is that the error variance, or the error that we're getting in these scores, is random and not systematic. So what the hell does that mean? It means that it's due to just fluctuations or issues with the scale. It's not something that's built into the scale that is going to bias the results. All right, so it's not biased, it's not systematic, it's not malevolent, it's not, you know, something. It's just, there's just variability that is the nature of sort of measuring things, and so the expected value of that really should be zero. It should cancel out. We're sometimes going to overestimate, sometimes we're going to underestimate. The long run average means we should be measuring things without error, and we really should be getting at the true score pretty well if a scale is doing a good job of trying to capture that true score. So in this sense, E, the error, and X are sort of random. They're sort of randomly varying things across people. T is a constant for at least for each person. Each time, you know, a person is sort of measured, their true score should remain the same. It should be unchanging. So it's more of a trait level thing, where X and E are both going to vary sort of randomly around the true score based on that sort of measurement error. Because functionally, we have the true score and people sort of varying around this is different people. So I start taking thing here. And then, so X is really just that same true score distribution with added variability to it based on error. It makes it vary a little bit wider. So it's just random variability of, it's T plus random variability of E together is what we get with X. That make sense? And so X and E are both sort of random variables, and by being random, we mean they sort of center around zero, which means there's no bias, and we're not sort of always under or always overestimating. It's sort of supposed to vary. So these are assumptions that we're making about these types of tests, these classical test theory derived tests. However, this idea is sort of theoretical, and it's really theoretically done sort of thinking about at the group level, everyone who's sort of taken a test. We don't really go through each individual person and sort of figure this out. We look at the sort of variability across people, and we know that there's variability that's due to X plus some variability that's due to measurement error, and that we want to try to separate those two out to get at the true scores for people. All right, questions so far? Have I completely left you all behind? Are you with me so far? It's all good? All makes sense? All right. Cool. So if you assume that people are randomly selected, right, randomly selected from a population, then T becomes a random variable as well, because they randomly vary across people. Therefore, in CTT, we assume that error is normally distributed, that our E is uncorrelated with our t. It's not biased. There's no bias. These things are independent. And we assume it has a mean of 0 because, again, it's not biased in one direction. We're not always overestimating or underestimating. It has a 0 bias because in the population, people are randomly being over and underestimated with the measurement error, so it sort of cancels out to 0. So we assume it has a mean of 0, has some amount of variability to it. We don't know what that is. We assume it's uncorrelated with the true score, and we assume often it's normally distributed. At least under classical test theory, we do. Under item response theory, we don't, which is why it becomes more complicated. All right, so say something, so I know that you're like there. I haven't heard anything for a while, so I get worried. Right. So there's things being sort of conflated there. There's like prediction errors, like if I'm trying to be tested on something as being correct or incorrect, right? There's sort of those kinds of errors. These are errors. These are like mechanical errors. So think about if you're trying to measure, again, if you have a scale, right? Your scale is supposed to be calibrated to a certain amount. If it's truly random error, the kind of error we're talking about here, that means every time you weigh yourself, it's somehow just not quite accurate. Sometimes it overestimates a little bit, sometimes it underestimates a little bit, but it's always sort of just this random unknown amount of variability. If, for instance, your scale is just always 2 pounds over what it's supposed to be, like just consistently 2 extra pounds, that's not measurement error, right? Because it's not random. That actually it's a miscalibration. It's an error in the sort of execution of the scale. That makes sense? So when people overestimate themselves, they're making errors, but they're measuring those errors randomly. That makes any sense. So the errors they're making in their judgment is different than the errors that's coming in through the measurement of that thing they're trying to get at. So there's sort of accuracy, and then there's measurement error, which is different things. Okay. Other questions? So let's say that for some reason, go back to the scale example. So let's say that if for some reason as the weight that someone puts on the scale goes up, the degree that it's off in measuring actually also increases. So if you're light, the amount that that it only adds an ounce. As the heavier you get, for every, say, 20 pounds, you get an additional ounce. So so there's error that's also then related to the actual true score. So your actual weight, there's a true weight that you have, but as that weight increases, the amount of error also increases, which means that the error and the true score are related. So what you want to see is that, if you're trying, think about in prediction. We do this with regression, how this sort of relates. We draw a prediction line and we say, okay, here's my prediction line. You can imagine that the points are. It has some amount of measurement, some amount of error of prediction around it. We expect there to be this amount of error in predicting our scores. Okay, so this sort of gives us a sort of buffer around this. And because this is consistent, it means it's actually unrelated to the actual predicted score, right? Because it's constant. With me so far? Because it's constant, it can't be related. If you started to see something like this, where down towards the bottom, I'm going to use a different color. If down towards the bottom, actually this is probably not different enough. Let me use pink. If down towards the bottom, the amount of error was very small, like this. So you think, and it got bigger as you went up, like that. all of a sudden now the error and the prediction start to be related. The bigger the prediction, the bigger the error is around it. So in regression terms and in even analysis of variance terms, this is called homogeneity of variance or homoscedasticity. We expect the amount of error to be consistent across the whole predictor. So this is X. We expect there to be a consistency in terms of errors across. It's the same thing with measurement. You know, if we're trying to look at a true score, which really, you know, for an individual person is here, and we add in this sort of measurement error, we expect it to be random and sort of based around the true score so that in reality it's positive half the time and negative the other half the time. And so it really sums out to being zero. What we start to see sometimes is that it isn't quite this way. It really looks more like this, right? So we overestimate way more, so it's not normally distributed. Therefore, it doesn't quite work very well with classical test theory because it's supposed to be normally distributed, right? Sometimes, again, with larger true scores, you get more error, and you start to get a correlation between error and true score, which doesn't work very well with classical test theory. Even the mean of zero, the normally distributed mean of zero thing really comes down to the fact that it's centered at the true score, so which means the mean of the error should be zero plus half the time minus half the time, so that you get a normally distributed value that centers around zero. It centers right around the actual true score. So that's why we want things to be normally distributed and have a mean of zero under classical test theory, and that's why the true score should be unrelated to the error. The error needs to be random. If anytime it's related to something, it can't be random. Okay. Questions? No. Hearing none, I'll assume we can go forward. That's good questions. What was the name of that study that you said a second ago? Hearing. There's a lot of interesting phenomena about people's perceptions of themselves. I think I might have mentioned this in here, but maybe not. Is this idea that like Americans in general overestimate their abilities by quite a lot. Like the average American will state something like they're better than 80% of drivers. Like they drive better than 80% of other drivers. So think about that. I'm sorry, it's 80% of people say they're better than 50% of the drivers. I think I got that right. Meaning the majority of people think that they're better than half of people when driving, which is not possible. Right? You can't, it doesn't make any sense. But they think so. They think that's true. And they tend to do that a lot with skills. So I think there's interesting that you're looking at so that perception in terms of the errors they make in self-perception is actually going to be high. The high, especially with American respondents, are likely going to make a lot more errors of one type in one direction. Okay, let's move forward. I need to mention this already. So measurement around error around t can be large or small depending on the type of scale you're using, the type of test you're using. The goal of designing most tests is to try to reduce the amount of measurement error, try to get cleaner, nicer, error-free test of some sort. But your test can vary a lot. You could have very little measurement error. It could be a lot. You can have a ton of measurement error, and it comes down to trying to figure out what's really going on. Trying to find the true score becomes more difficult the more error there is. All right, so we're trying to reduce the amount of measurement error that exists in scales so that we can actually have an easier time of trying to identify that true score. All right. So another central component. So we got this idea of the true score model. Every scale is true score plus error. Every question, every scale, everything. So another way of thinking, another central sort of tenet of CTT is something called domain sampling theory. So it's another theory, but it's sort of, we can think of it as sort of within the idea of classical test theory. It's another way of thinking about populations and samples. So you probably heard a lot about populations and samples before. But usually those terms are used strictly when describing people. You have a population of people, you want to randomly select people from that population into your sample, and then sort of test them or whatever, electroshock therapy, then whatever it is you're going to do to them to see if there's a difference between people or whatever is part of your experiment. But that's not the only way we can think about populations and samples. There is a type of analysis that people use called random effects analysis. So normally we're used to thinking about, if I want to do some experiments, I have a treatment group and a control group, and that's it. Or maybe a couple treatment groups and a control group. But let's say I'm doing a drug trial, and the typical amounts of the drug can be somewhere between 10 and 500 milligrams as typical doses, depending on the severity of symptoms. I could design a study where I look at 100 milligrams, 200, 300, 400, and 500 versus control, or I can think of that 10 through 500 as a population of potential milligrams, and then randomly select them out. So I now have people that are being given 27 milligrams versus 110 milligrams, 347 milligrams, right? So there's a random selection. And what that does, it helps to generalize from your sample of interventions, treatments, to the population. So that's something called a random effects ANOVA. It's not what we're talking about here, but it does expand this idea that what a population is and what a sample is not strictly, not just restricted to people. It can be restricted to a number of different things. Okay, another way of thinking about populations and samples. So a domain is a population or universe of all possible items measuring a single concept or trait. So this is like theoretically infinite. It's just like a population of people is theoretically infinite. Okay, so theoretically we're talking about every possible item or question that could be used or could be written or could be designed to measure a particular content area. So that could be depression, could be math ability, it could be history knowledge, it could be whatever you want. It oftentimes has to be specific enough to not just be ridiculous, but it has to have some kind of domain with which you're trying to target with our question, something we're trying to measure. So, in that case, the domain is sort of the population of all potential items that could be included in that domain, and a test, an individual test, like the Beck Depression Inventory, is a sample of items that are taken out of that universe, out of that domain. So the domain now is the population. The test is now the sample of items that you can have people respond to and use as a representative of the domain, of the population of all possible items. Okay, so far? So it's a diagram. It looks something like this. You have, just same way with anything, you'd have, some domain of items. All right. And then you would take, in some way, some kind of process here to then pull out a sample of items from that domain that we would call the actual test. So as an example, all right, this could be depression. Every conceivable question related to depression is in this domain, and the test is, the one that you have for your homework, like the CESD, the Center for Epidemiological Studies Depression Inventory. This is our sample of items taken from this domain. With me so far? All right. So think about this idea a little bit. So most of the time when tests are developed, like the Beck Depression Inventory or the CESD or whatever, they're done like this a little bit. They'll generate a bunch of items that are supposed to represent the domain. They'll test them out, find the ones that work best, narrow it down to a specific test they want to use, and then sort of verify that with other studies. They don't typically go back and keep re-pulling things from the same domain, but they can. Where this becomes a little more realistic, or you might have an analogy that works, is this process maps on pretty nicely to, when we talked about last time, to the computer adaptive testing. So CAT, computer adaptive testing, like the GRE or SATs or other things they've done, this computer adaptive, they have to have a domain of a bunch of items that and they know those items' properties, like how difficult or whatever, and what those items are measuring. So the domain here would be not necessarily the whole GRE, but say this could be the sort of verbal part of the SAT, right? All verbal sort of skills and knowledge, and then you get your version on the SAT of the verbal questions, and that's your test. And your test may be very different from other people's tests, and the only reason why that works is because they're all coming from the same domain of which they have items with known properties. They can pull them out and then sort of make them work across, like, to match them across people to get the same scores. So computer adaptive testing uses this very idea that there is some bank of questions around a particular domain that can be pulled from to create different versions of tests and have multiple different versions of tests so that people can't cheat. There's even if you do it multiple times, you don't get the same items, so that there's no testing effect, no other things like that can help your score, right? It really is measuring ability and not just practice or something like that. Questions about that? So this maps on directly to, you got a population of people that's huge, and you're taking them out into a sample of people that you're actually going to study. Same idea. Huge sample of items, and we're pulling those out to give one particular test set of like 20 items that measures depression or whatever, and we're going to give those to people and sort of use that as our measurement tool. Okay. So with this in mind, we can talk about some other ideas about how reliability and stuff works. All right. Okay, so to tie in the domain sampling theory and true score back together, a person's true score, right, could be or would be obtained if you had them respond to every single item in the universe of items. So you have a domain, it's got infinite number of questions. Let's say for the sake of argument, it's just a large number, like 10,000 questions or something. And you go through and they would have to take all of them to figure out their exact true score. However, we only see responses to the sample and not to every single question, right? So reliability, when we think about what reliability means, the reliability of a test is its ability to capture the universe of items with just a few items on the test. How well? So if you think about it, if this were people, you got a population and you got your sample, our ability to infer meaning back to the population or to generalize back to the population is the same thing here in terms of the reliability of the items on a test is how well those items can reflect the true score as represented by the population or the domain of all items measuring that domain. Okay? So far, pretty good. All right. Okay. However, the domain is made up of an infinitely potentially large bunch of items. So as tests get longer, they're likely to represent the domain better. Therefore, in terms of classical test theory, longer tests should have higher reliability, right? The longer the tests are, and this is the same mentality or thought process we go through when we take samples from a population. The bigger the sample is, we think the more representative that sample is of the population. Same thing here. Longer tests mean that better representation, better coverage of the kinds of items in the domain, so longer tests are better, right? Also, if we take multiple random samples from the population, we can have a distribution of sample scores that represent the population, and we can start thinking about things like in terms of sampling distributions of means of tests, not just of people. We can also do it for tests as well. We start thinking about this more theoretically. Apply what we know about populations and samples of people, apply those to test items and domains, and it starts to sort of parallel things. So each random sample from the universe would be then randomly parallel to each other. What the hell does that mean? If I have an infinite number, or some large, 10,000 numbers of items representing a domain. So think about every conceivable way you can ask somebody about depression, right? We can just go through just tens of thousands, slightly different variations, lots of different things we can ask about. If we just randomly took 10 questions at a time to measure depression as a test, as an inventory, each one of those would be a different reflection, a different version, slightly different sample of items from the population of items, but they'd also be similar to each other. Whatever you score on one of those should be similar to what you score on another one of those, right? So your scores should be similar. They're not going to be exactly the same, but they should be sort of similar across all the items, which is what they mean by making them sort of randomly parallel. So because they're random samples, they're going to be covering different components of the domain, but being random selection of items from the domain is going to make them all sort of parallel versions of tests from that domain. So from that, we can actually get an unbiased, this is important, unbiased estimate of reliability if we simply just added up, if we took the correlation between every single that item and the average correlation it had, that scale, that test, and actually go through and correlate that test with every other test that comes out, we can get an average of that, and that'll tell us how well that test reflects the true score. Right? So think about, let that like wash over you for a second. Think about that. So let's see if you got any questions. No. So this is assuming that you have done that. So this is assuming, like in a very concrete way, you actually generate all these items, right? And then you take random samples of items from these, from the domain to create different tests, right? And you got to think it's almost like an infinite number of combinations of those things. We can figure out how well any one test captures the true score by simply looking at the average correlation that test has with all other parallel tests. That average correlation will tell me, well, on average, this is not doing a very good job of being similar to other tests, or it is. If on average it actually is capturing or doing very similar types of, it's measuring a very similar type of response from people, it's going to reflect it's actually being fairly consistent and capturing that true score fairly well. So is anybody actually doing this? No, this is like sort of thinking theoretically. If we were to do this stuff, we can actually figure it out. We can get an unbiased estimate by simply looking at the average of that one test with all other versions of the test of the same size, get that average, and we can actually then get a measure of reliability, how much that test corresponds or correlates with the true score that you're trying to target. Of course, nobody's going to do this. This would be, if you already have a domain created of all these items and all this craziness, doing all this stuff seems sort of crazy, right? It'd be like overkill. But it's a first step sort of theoretically. If we were able to do this, this is how we would sort of figure it out, right? So we're not going to do that, obviously. But so reliability is theoretically the correlation between a test score and a true score squared. So we're trying to figure out what the relationship is between any test score that we have and the true score. That's going to give me this sort of correspondence. We're going to get the variance of the true score, because remember the true score is going to be x plus e, right? Which means that this corresponds to this, this is x plus e. So this over this, we got the true score plus error. So we can actually start to figure out all right, identify what this error looks like and remove it to actually get the idea of how much the true scores actually correspond. We can't measure this directly, again, because if we knew this stuff, we wouldn't need to make the test. We'd be able to measure everything sort of directly. But if this were true, we can actually figure this out by figuring out, okay, what's the variance of the true score, divide it out and actually figure this out. But we can't. So the way around this is reliability can be viewed as a measure of consistency or how well tests hold together. So go back to this for a second. So this is the variance of the true score, and this is what we don't know. What we do know is X. We don't know this, but we do know X. So how can we try to identify what part of X is actually due to error? Well, there's different ways we can try to figure that out. There's different ways of trying to target this error portion and actually pull it out and get what really is going on true score wise by looking at the percent of variation in the tests we're interested in with other tests under different assumptions. So let's think about what that means. So reliability can be viewed as a measure of consistency or how well a test holds together. So if a test does a good job of being consistent, it means it's consistently measuring the same thing. So the consistency part is the reliability. Now, whether or not it's measuring your intended true score, your intended target, that's validity. Okay? So validity is how close you're getting to the target. Reliability is how consistently is that thing being measured. So if a test holds together, meaning that it consistently measures the same thing, and you get the same score on that test over and over again, we can say it's reliable. So I'll give you an example of that. If you set your watch a half-hour fast, right, and assuming that the watch is calibrated correctly, that watch is reliable. Right? It's giving you a reliable time that's 30 minutes off every time you look at it, but it's reliably giving you the same wrong number every single time. So it's reliable, but it's not valid because it's giving you the wrong time. All right, so consistency across time or across people or across versions, there's different ways of thinking about it. All are ways of looking at reliability. It doesn't answer the other half of the question is, are you measuring what you intend to measure? That's validity. That's a different question. So we're starting first with the reliability question. We can get at this idea of reliability. It's measured on a scale of sort of 0 to 1, sort of like a correlation, but it's only positive because everything's sort of squared. The greater the number, the higher the reliability. So we typically want scales, tests that we're using to have a reliability of about 0.8 or more, which means that it theoretically shares 80% of its variability with the true score that you're measuring. So if we can figure out that a test has a reliability of about 0.8 or more, that means that it's actually, that's the sort of minimum threshold we think of as being reliable. It also means that it contains 20% error, right? So 80% reliable, 20% error. If it's 90% reliable, we're only talking about 10% error. But it's a way of sort of identifying the parts of the variability that is consistent. And it's a way of identifying how much measurement error we have by looking at the part that isn't consistent. So the whole process here is how do we try to figure out how to pull the measurement error apart from the real thing we're trying to measure. So that's how we're looking at sort of reliability. So this idea of a reliability index, we can actually measure reliability. And again, we never know the true score. So we have to figure out ways around it. How do we get around not knowing the true score, figure out the reliability of items, separate out the measurement error, and sort of see what's going on with these items without knowing what the true score is exactly? Okay. So there's different ways. So the different ways that we do it can depend on how we're trying to estimate the true score and where we think the source of measurement error is coming from. So that's why we will look at test-retest reliability, parallel forms reliability. Split half and parallel forms are essentially the same thing with a different focus. And then we get a different idea of internal consistency, which I had mentioned before, is this idea of Chrome box alpha. But they all sort of look at covariance, correlation, and things in different ways to try to figure out if items are consistent or not. Okay. Questions so far? All right. So first, let's talk about test-retest. It's probably the most common, and it's fairly simple to do. It can be kind of a pain in the butt, but it can be simple to do. It assumes that everyone that you measure has to come back and be measured again. All right, so it's test-retest. They got to take the test once, they got to come back at some point and take it again, and then you can actually correlate those two time points of the same measure and get an idea of how reliable it is. So this evaluates the error. So when we're looking at measurement error, we believe that time, like when you actually take it and repeated sort of measurements, actually add to the sampling error, the measurement error of the test. So we're trying to identify the sort of time sampling error that gets built into the test by having the test being taken multiple times and then trying to identify the consistent components of the test-retest items. It's pretty simple to do, at least simple theoretically. Give a test at time 1, give same test at time 2, calculate the correlation for the two scores, and voila, you've got the reliability. That's it. Easy to do. One test does it all. You just need one version of your test. So you got this huge domain of items. You pull one sample of those out, theoretically. You give it once, you give it twice, you correlate it, and the higher the correlation is, the more reliable that that test is. Pretty simple. There's a couple of issues. I mean, it makes it sound super simple, and it is, except how far apart they are can make a huge difference. So if I give you a test today, I give it to you again tomorrow, it's going to be a lot more reliable than if I give it to you today and give it to you again in a month, or in 6 months, or in a year, or 5 years, right? The longer the time period is between the time points, the less reliable it's going to look. So you're looking at something like math ability, where kids take like a math aptitude test, say in like 7th, 8th, 9th, 10th, 11th, 12th grades. It's really hard to think about reliability that way, because you're talking about a year difference between every single one of them. So it has to be something that's super stable. It doesn't vary very much from day to day. But you think about something like depression. If you were to give people depression measures every year for 5 years or something like that, they probably wouldn't look very reliable, because people's amounts of depression change. You know, there's some state level factors that are going to contribute to to depression and things. So choosing the time frame can become very important to showing whether or not your measure is reliable, right? So that becomes, if it's too short, like if I give it to you now and I give it to you again in 2 minutes, it probably, it's not super useful either. So you got to sort of pick a window that is good. So if you assume two administrations of X1 and X2, assuming that X is the same, that X is the scale, and we're doing X1 and X2 as at two different time points. Same test, two different time points. What we see is that we expect X1 and X2, the scores for these two, to be the same. We expect the errors to be the same as well. There's no reason to believe that the errors are going to be the same. The only thing that's going to be different is the time between the two of them. That time sampling error, the longer the time is between them, may add more error here, but we still expect the measurement error to be about the same. So the correlation, this is rho, between the administration 1 and administration 2 can be seen as the covariance between the two of them divided by just the variant, or the standard deviation of both of them. I know it's written in Greek letters, but it's essentially the covariance between the two of them over the standard deviations of each. So because these two things are measuring the same thing, the covariance between the two of them should be just the variance of the true score. So again, they're both measuring the same true score. So the covariance between the two of these should be the portion that is reflected in the true score. So it's the variance of the true score. Because these two things should have the same variance, same error variance here, the multiplying these two standard deviations should be the variance for X. So it simply take the covariance between the two of them over the variance of them, of the scores. I should get the correlation between the actual test and the true score. And this gives me a sort of measure of how much of the true score this scale is actually covering, which gives us the sort of measure of reliability. So there's a fancy way of saying if I correlate the two administrations, the degree of correlation between test and retest should be capturing the true score and give me an idea of how reliably not only is it going across time, but what percentage, what amount of the true score that scale is actually measuring by just simply looking at the same test twice. There's a lot of shoulds here. Again, we're assuming that the expected value should be the same. We're assuming the errors should be equal. There's a lot of things that are assuming, and if you actually can show that this is not true, then this ends up not being the case, right? But if we can assume it, there's no reason not to assume it. Then what we find is that the correlation between these two, the correlation between the two variables, the test one and the same test at time one and time two, will give us an estimate or a measure of the reliability of that scale as it reflects the true score in the domain. Row of xt. Wait, where's that? Oh, row of t. Row of x1 here, and then row of xt. Okay, so this is basically a fancy way of saying, therefore, right, the correlation between x1 and x2 really reflects the correlation between x and the true score. Okay, so if I correlate my test and retest scales, that should estimate for me, to give me an idea of what the correlation between my test and the actual true score in the domain. So row x1, x2 is a correlation between the two, pre-test and the time one and time two measures, and then the row xt is just saying that it should be reflecting the correlation between the scale that the sample you've pulled out of the domain and the true score that's being measured by that domain. That's why it's a measure. That's why test-retest reliability is a measure of reliability and measure of the reflection of the true score. Sure. So think about that. So this is why we covered correlation, today and on Tuesday. So how do we calculate correlation? So the correlation between time one and time two is going to be the covariance between time one and time two over the standard deviation of time one times the standard deviation of time two. This is just the definition of correlation, covariance over the two standard deviations multiplied, right? So we had written it this way. Let me rewrite it the way we did it before. So if I have x1 and x2, this is the covariance of x1 and x2, the two different times, the test and retest versions of the test, right? I would divide that by the standard deviation of x1 times the standard deviation of x2, the two different time points. This is just the same thing written out with Greek letters, because it's still talking sort of theoretically and not actually. But so we replace this with covariance, replace that with S, replace that with S. You get the equation we talked about earlier today and on Tuesday, that if I want to get the covariance between the correlation, right? What I want is a correlation between x1 and x2. I would do that by getting the covariance between the two of them, the amount of shared variance between the two of them, and standardizing that based on both of their standard deviations. Okay, so that's just this part. How do we go from here to here is sort of a theoretical sort of leap. What this is saying is the covariance, what the part of x1 and x, so let me ask it a different way. Why would x1 and x2 be related? What's driving the relationship between x1 and x2? So if I give you the back depression inventory today, and I give you the back depression inventory again a week from today, right, as a class or as a group of 40, 50, 300, whatever people, I give a test and a retest of the back depression inventory, and there's a high degree of covariance. They share a bunch of variance between the first time administration and the second time administration. Why are they similar? Why are the responses similar to one another? or why are we assuming they are? We're assuming that your level of depression is driving your response to both of those things, right? This is true for if it was math ability. If I give you a stats test today and came back and give you a stats test next week, the degree to which your responses are similar should be driven by your actual math ability. All right, so the reason why we have any covariation between x1 and x2 is because it's being driven by the true score. So this covariance between x1 and x2 really is just the variance of the true score. So this covariance is really just the variance of the true score. The amount of variation they share is just that each one of them are reflecting the same variance in the true score across people. All right, so that's why this is really just this. Well, because x1 and x2 are the same measure, the 1 and 2 just represent time. It's just the standard deviation of x, standard deviation of x, they should be the same. We said that up here. We expect them to, the variances to sort of be the same, expected values to be the same. Since they should be the same, it's just the variance of x times the variance of x, which is just x squared. Not x squared, sigma squared for x. It's just the variance of x. So the covariance over the two standard deviations really is just the same thing as looking at the variance of the true score, because that's what's driving this covariance, over the variance of x, because x is just the same thing measured at time 1 and time 2. So because of that, the relationship between x1 and x2 as a covariance really reflects the relationship between that scale and the true score variance. It tells me how much variance that scale, that test, shares with the true score variance. When I say true score variance, I mean variance across people, right? Because we're not just doing this for one person. It's a group of people we're giving the test to, bringing them back, give it to them again. So there's going to be certain variability across those people, but what's driving that is their variability in true scores, and this test is trying to capture that to some degree. So this row here is telling me that the correlation between x1 and x2, really the covariance between x1 and x2, right, is just a reflection of the covariance correlation between x and t. This is the sort of theoretical connection between the two of them. Yep. So because the question here is why is it if I just correlate a test retest of the same test, right? How does that reflect reliability relative to the true score we're trying to measure, right? So why is correlating the test and retest a measure of reliability? Because the amount of covariance that is shared between the test and retest reflects the variability in the true score. These two things are the same thing. Because x is the same thing measured twice, it should have the same standard deviation. So when we multiply them across, we're getting just the variance of x. So if we correlate the test and retest of a test, that we create from the domain, it's the same thing as looking at the ratio of the true score variance over the variance of x, which will give me a correlation between x and t. Across people. Because that's the thing. We can't actually identify the true score and error in individuals. All we really can do is try to separate out what appears to be error variability across a sample of people, pull it out and say, okay, well, if we know there's this much error, meaning we're able to figure out how much this overlaps with the true score, we can then figure out how much error there is. That error variance is going across people and is considered random. We can then sort of figure out at least what proportion of the true score variation across people is accounted for by the variation of this test across people. Because in order to do a covariance or a standard deviation or any of these things, any of these parts up here, I can't give the test just to one person because it won't tell me anything. I won't be able to tell what parts are true score and what parts are error or any of that kind of stuff. I can't correlate anything. I can't do anything if I just have one response to both tests. So that's what I was saying earlier, that the problem with classical test theory is, one, it depends on the items on that specific test, right? So X is a very specific set of questions. I can give that pre-test, post-test, and that'll tell me sort of the degree of relationship. But it also is very specific to that sample of people that took it. So I give it to one set of 300 people, and they come back a week later and take it again. I can then correlate the pre and post test, or the time 1, time 2, the test, retest values of that. It'll then tell me how much that test reflects the true score, but it's the true score across all the people. So it's just a way of looking at variance. How much of the variability in the true score is being captured by the variability in X across people? All I know is that if someone is high at pre-test or high at test 1, they're high again at test 2, they likely have a high true score. If someone's low at pre-test or test 1, they're low at test 2, they probably have a low true score. I don't know what the true score is, but I know that it's likely low because they scored low both times. They scored high both times. They scored in the middle both times. What starts to happen, though, is where you start to get the error is, you got a person who scores high at time 1, they scored low at time 2, so now it's sort of difficult to figure out their true score somewhere in between there. It becomes a little more wishy-washy. It becomes a little harder to figure out exactly what it is. If everyone scored perfectly consistent, right? They're the highest, they're the highest again. Next highest, next highest. They're perfectly consistent all the way down. This would be 1. Be perfectly consistent, zero error. We would know that the scale perfectly captures the true score. That's usually not the case. There's usually going to be some flip-flopping around where people are scoring in those different time points. They're going to add to the measurement error. They're not going to be perfectly consistent, but we at least can capture how much of that variability is consistent across time. And that's going to tell me the percent of variation in the true score that is captured by X. It's not telling me what the true score is. It just tells me how much variability in the true score relates to the variability in this scale. And I can know that it's reliable. Again, it doesn't tell me if it's valid. It just tells me that it's reliably measuring the true score. That makes sense? So if you're thinking that it's going to tell us what the true score is and how good a job we're doing at capturing that true score's accuracy, it's not doing that. It's just saying that if I know that someone responds consistently across time 1 and time 2, whatever that's measuring, it's measuring it consistently. It's capturing a consistent portion of that true thing, of that domain we're trying to measure. Now, we could be barking up the wrong tree. We could be, those items may be measuring a different domain than we intended, right? And that's a validity thing. But at least here, it's telling us how consistently people are scoring, which then tells me what percentage of the true score is being captured by our scale. So consistent scoring across time tells me how consistently my scale captures the true score. So if this seems confusing, and you see like I'm spending a lot of time on this and trying to really get this down, it's because it is. This is confusing. It's like, wait, why, what? I remember the first time someone was trying to tell me like, oh, if test-retest reliability tells me how well the test is doing in measuring the true score. I'm like, what? That doesn't make sense. Just because it's consistent doesn't mean it's correct. They're like, exactly. It's two different things. Being consistent is different than being accurate. So right now we're just worried about how consistently is things being measured, and if it's consistent, meaning there's a high correlation between time 1 and time 2, the test-retest scores, that means at least it's consistently measuring the same thing, the true score. What the true score is, we don't necessarily know yet, but we know it's consistently measuring the same true score that's attempting to be captured by that scale, by that test. All right, so test-retest reliability is a measure of the reliability of the scores coming from a domain because the shared variation between the time points tells us how much variance that scale shares with the intended true score. And that you may need to like sit with that, like, you know, infest your brain for a little while until it starts to really make some sense. Because I remember the first times I remember seeing them, like, that doesn't make any sense. But and this is where, like, if you do have the book, or just Google test-retest reliability and read some other people's sort of, you know, takes on it, and you'll see a lot of the same stuff. There'll be people that go way more technical into the mathematics and all that kind of stuff, which is not necessarily where you want to go. Even if you do, it might help you if you like that stuff. But just in terms of theoretically, what is intended with the test-retest reliability, and it's really just trying to capture what variance can we identify as being related to the true score. In this case, what we're doing is we're identifying what part is actually error, what part seems to be sort of random noise. Because if we correlate the same test at time 1 and time 2, and we find out that this has a correlation of 0.8, that tells me that there's 20% of the variability that these tests do not share. I at least know that means that there's 20% of the thing we're trying to measure that this test is not good at doing. Right? That there's some portion of variance that is not being captured because it's looking like there's some inconsistencies between their responding. So the best I'm going to do at capturing the true score with that test is about an 80% coverage of the variability. All right, see, you guys love this stuff. Staying after, not saying anything that's way late. Love it. Actually, well, no, there's a if you look up the authors, and there's a rental, an online rental. It's like $30. And you'll get access to it immediately. It's just an online thing. You know, basically, it's just a textbook as like a PDF, fancier. And that's perfectly. That's the way I would suggest going, just because it's the cheapest route by far. It's a rental because I think you have it only through like October, which is way longer than you need it for. And you know, and if you can find copies or versions of the book that's older, that's good too. But again, it's going to take a while to ship. So that, you know, if you're willing to spend $30 on an e version of the book, that's a way to go. And it's going to be hard. I mean, you can probably find used ones cheaper than that, but not by much. I wouldn't think. Yeah, $4 is definitely cheaper. It's probably an older edition, which is totally fine. There's really no reason not to go that route, but it depends on where it's coming from. It might take you a while to get it. But Google is your friend. You know, like, go on Google and put, topics that seem confusing. Put test-retest reliability. Put classical test theory. Put domain sampling theory into searches and just see what you find. You're going to find you'll find YouTube videos of other people talking about this stuff, and they may explain in a way that that is different than my explanation and might register with you a little better, or you may watch that and come back and go, man, his way of explaining was way the hell better than the other person's, or whatever. It could go a lot of different ways. Anyway. Yeah, Khan Academy is a good place to go. Don't put too much sort of. Let's just say, like, I've gone through and checked Khan Academy stuff for use as supplementary materials, and their stuff is great. Sometimes it's not. So yeah, I would definitely go there, but be critical as you're sort of going through the videos and stuff, and don't take everything at face value. Sometimes they do some weird stuff. But yeah. So you can definitely get through this without the textbook or without whatever. Just go and supplement your idea, because sometimes all it takes is just to hear a couple different perspectives on something that's complicated, and it'll start to click. It takes just a couple different perspectives on things. So I think it's good to have the book. If you don't have the book, then Google some stuff through Khan Academy or through YouTube, or just find some PDFs documents that talk about this stuff and just read through it. That stuff could be all you need to fill in the last little blanks to sort of click. And also, we're talking about it now. We'll come back and sort of revisit this again. You may see that just in time, it just ruminating in your brain without even really thinking about it, you may come to a better understanding all by itself. Sometimes you got to go away from a topic to have it sort of solidify in your brain when you come back to it again.